So this lesson is on proportional segments between parallel lines. In a few minutes, I'm going to ask you to open up your textbook to the investigation in this section, so you might want to get that going now. So the question for the day is, how do parallel lines create proportional segments? I mean, we've been dealing a lot with similar triangles, and we know a lot of proportions come from similar triangles. So let's talk about some when we have parallel lines and not necessarily triangles. So first we're given that OE is parallel to NL. So I'm going to mark those as being parallel. Now we know why these two triangles are similar. If we have parallel lines, we have corresponding angles. You might say that angle M is a shared angle. So by the angle-angle conjecture, we could say that triangle MOE is similar to triangle MNL. So take a minute now and determine what the length of LE would be. So did you find that since the triangles are similar, we could write a proportion perhaps of 48 is to 60? That's going to be in triangle MOE. And then if we take the entire side MN, that is a length of 84. And the other side ML is 60 plus Y. We do our cross multiplication. We get 2880 plus 48y equals 5040. When you solve that equation by subtracting 2880, dividing by 48, you should get that y equals 45. Now, let's compare this ratio. LE, we said, was 45. ME is 60. 45 over 60. And we want to compare that to NO to MO, which is 36 over 48. Maybe you want to cross multiply those, or maybe you want to reduce them. Do you notice that they are equal? That's pretty interesting. So what do you think? Is that a sheer coincidence, or do you think it's a mathematical rule? What I'd like you to do is to complete steps 1 and 2 of investigation number 1 on page 624. You might want to hit pause and work on this, and then when you come back, press play. So you answered a few questions. What do you notice about the ratio of the lengths of the segments that have been cut by these parallel lines? Did you notice that the parallel lines divide those sides proportionally? That's pretty cool. That's going to be our conjecture for the day. The parallel proportionality conjecture. If a line is parallel to one side of a triangle, or a line parallel to one side of a triangle, passes through the other two sides, it divides those two sides proportionally. Now the converse of that, let's say we have a line that cuts two sides of a triangle proportionally. Then it must be parallel to that side. So if we have a triangle and we draw a line that is parallel to that side, and if we call those sides A and B and call those C and D, we can say that A is to C as B is to D. Very nice. So let's play with that conjecture for a little bit. So we have this diagram below. We're told that E and B are points on the sides of the triangle, and we're told that EB is parallel to DC. So if AE is 3, ED is 6, and BC is 8, find the length of AB. So we probably went 3 and 6, and we said BC was 8. Let's call AB's length X. We have two parallel lines, two parallel segments. They divide the triangle proportionally. So perhaps you could write 3 is to 6 as x is to 8. Solving that, we get x is 4. Things look good. So it is a similar diagram, but we're going to look for a different side length now. Again, AE is 3 and ED is 6. This time DC is 15. Find the length of EB. So let's be careful here for a minute. If AE is 3 and ED is 6, and DC is 15, one thing to notice here is that while we know that the lines are parallel and they divide the sides proportionally, they do not divide the parallel sides proportionally. So we still might want to think of our similar triangles here, where we have this green triangle and then we have this red triangle. So if you notice that, what you might see is that the ratio of 3 to 9, I'm using side AE and comparing it to side AD. So 3 is to 9 as x is to 15. And when we solve that, we should find that x is equal to 5. So the length of EB is 5. So let's prove why this is true. So we're going to start with our given, that we have a triangle and we draw a line parallel to a side of the triangle. We want to prove this proportion, that A is to C is the same ratio as B to D. And again, let's assume that they're non-zero lengths. That way we don't have any zeros in our proportion, because that does scary things. So why don't you pause for a minute. Think about if you could write this proof. Don't worry, I'll wait. Okay, let's see how you did. So I'm given that triangle with the parallel sides. So one thing I might think about right now is that my two triangles here are going to be similar. So I'll say that triangle, I should actually say why those are parallel. Since XY is parallel to BC, I have angle AXY congruent to angle B, angle AYX congruent to angle C by the corresponding angle conjecture. So that tells me that my two triangles, AXY, is similar to ABC by angle. So now I know the sides are proportional. So I'm going to write a proportionality statement, then I'm going to do some algebra. So by that CSSTP, corresponding sides of similar triangles are proportional, it tells me that A is to the whole side A plus C. A is to A plus C, as B is to B plus D. So let's do some multiplication now. Let's multiply these out. I'm going to get A multiplied by B plus D. And that's going to equal B multiplied by A plus C. Well, it looks like I should distribute, so let's do our distributive property. That gets me that AB plus AD equals AB plus BC. Now, do you notice that there's an AB on both sides of the equation? So if I simplify this equation, I get that AD is equal to BC. And then the converse of our means extremes property, don't you love that means extremes property? It says that if I'm multiplying A times D, they're going to be opposite each other. And the same with B and C. And this is what we're trying to show. So this is the reason why when a line parallel to a side of a triangle is drawn, it divides that triangle proportionally. Moving on, we have our extended parallel proportionality conjecture. Suppose we have two or more lines passing through sides of a triangle that are parallel to a side. Won't it just divide them proportionally as well? So let's see if we can solve for P and for Q. So perhaps you solve for P. If I look down here, I almost see a proportion here. I almost see that 3 is to 4 as 4 is to P. 3 is to 4 as 4 is to P. So when I cross multiply, I'm going to get P is equal to 16 over 3. And if I want to find Q, I can almost write another proportion just like that. What if I say 2 is to 3 as Q is to 4? And likewise, Q is equal to 8 over 3. So we can extend it to even more parallel lines as well. So hopefully this lesson on parallel lines drawn through sides of a triangle and dividing those sides proportionally will help you in your future similarity problems.